Hi everyone. In this video we are going to discuss about the statistical independence. So here we are going to consider some events and the independence between those events. So coming to the definition of statistical independence, here is one definition, that is, if probability of A given B is equal to probability of A, or probability of B given A is equal to probability of B, we say that the events A and B are statistically independent. So from the first equation, that is probability of A given B is equal to probability of A, that means that given condition of B doesn't have any influence on the event A. That means we can say A and B are independent. Similarly, in the second case, probability of B given A is equal to probability of B means the event A, that is a given condition, doesn't have any effect on the event B. So in that case also we can say A and B are statistically independent. So either if probability of A given B is equal to probability of A, or probability of B given A is equal to probability of B, we can say the events A and B are statistically independent. So we begin, if probability of A given B is equal to probability of A, then we can write probability of A intersection B as probability of B into probability of A given B using the multiplication theorem of probability, which we have discussed in the previous video. So from there, it is given that probability of A given B is equal to probability of A. So probability of A intersection B can be written as probability of B into probability of A. Similarly, we can write probability of A intersection B also in terms of probability of A into probability of B given A. So from there, we know probability of A intersection B that we got as probability of B into probability of A. So from there, on equating that both LHS and RHS, we will get probability of B given A is equal to probability of B. So the first equation, probability of A given B equal to probability of A, is same as that of probability of B given A is equal to probability of B. So if any of those equations are valid, then A and B are statistically independent. So from both these conditions, we have another condition, that is, if A and B are statistically independent, then we can say probability of A intersection B can be written as probability of A into probability of B. Similarly, we have another definition, that is, events A and B are said to be independent if probability of A intersection B is equal to probability of B into probability of A, or probability of A into probability of B. So for that, we know probability of A intersection B can be written in terms of A B given and A given B using the multiplication theorem of probability. So that definition is written here. Since if A and B are independent, then we know probability of A intersection B can be written as probability of A into probability of B. Then either we can write probability of A into probability of B. We can replace probability of A intersection B by probability of A into probability of B, which is equal to probability of A into probability of B given A, from which we will get the definition 1, the conditions of the definition 1. So if events A and B are said to be independent, then we can write probability of A intersection B is equal to probability of B into probability of A. And similarly, we can also see that if probability of B is equal to probability of B given A and probability of A equal to probability of A given B, then also these events A and B are independent. Next it's a statement that the mutually exclusive events cannot be independent. We know by the definition of mutually exclusive events that if two events, like the happening of one event hinders the happening of the other event, then we say those events are said to be mutually exclusive. So in that case, there is some independence, right? No, there is some dependence, right? Happening of one hinders the happening of the other, or prevents the happening of the other. So if A and B are mutually exclusive, we can say A intersection B is a null set, because it won't happen simultaneously. So we can say probability of A intersection B is equal to probability of phi, which is equal to 0. Now, probability of A given B can be written as probability of A intersection B divided by probability of B using the multiplication theorem of probability, and from which we know since the numerator probability of A intersection B is equal to 0, probability of A given B will be 0. Similarly, probability of B given A will also be 0. But that is not equal to probability of A or probability of B. Why? Because A and B are two events and it has some probabilities. It is a non-zero event, or like it's not an empty event. A and B have the probability that is greater than 0. So, A and B cannot be independent if they are mutually exclusive. Now, in the previous section, we were discussing about the independence of two events. So, if two events are A and B are independent, then probability of A intersection B is equal to probability of A into probability of B. Now, when it comes to the independence of three events, there are two conditions. So, the condition for the mutual independence of three events are the following. The events A, B, C are independent if they are pairwise independent and they are totally independent, like probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. So the condition 1 is a pairwise independence, that is probability of A intersection B is equal to probability of A into probability of B, probability of A intersection C is equal to probability of A into probability of C, and probability of B intersection C is equal to probability of B into probability of C. And the next one is probability of A intersection B intersection C is probability of probability of A into probability of B into probability of C. So here, only if these two conditions are satisfied, then only we can say that these three events are mutually independent. Otherwise, if it satisfies only the condition 1, then we can say these events are pairwise independent. Now, in case of three events or more events, we cannot say the pairwise independence does not imply mutual independence. So, first condition and second condition has to be satisfied simultaneously. Only then will these events be independent. So, to show that the pairwise independence does not imply mutual independence, we can show it using a counterexample. So here is an example. We consider an urn containing 4 tickets with numbers 110, 011, 101 and 000 written on them. So we have 4 tickets. So suppose a ticket is chosen at random. So we have with us 4 tickets and we have to choose 1 ticket at random. So each ticket has a probability 1 by 4, has an equal chance. Now let A, B, C denote the events that the number on the chosen ticket has the digit 1 at the first, second and third place respectively. So for the event A, the chosen ticket must have 1 at the first place, and for the ticket B, 1 must be at the second place, and for the ticket C or for the event C, the ticket must have 1, the digit 1 at the third place. Now, since event A is a ticket with number 1 or the digit 1 at the first place, we have 2 tickets, that is 110 and 101. So each ticket is chosen with a probability 1 by 4. For here, since there are 2 tickets, we'll get the probability of A as 1 by 2. Similarly, we can get probability of B and probability of C also as 1 by 2. So for all those events A, B and C, all those has probability 1 by 2 each. Now, probability of A intersection B. The probability of A intersection B means probability that the ticket with the number having 1 at the first and the second place is chosen. So, the number 1 at the first place and the second place. So, that number is 110. So, that ticket number is 110. So, that is 1 by 4. Similarly, we will get probability of A intersection C and B intersection C also as 1 by 4, where we will get only a particular ticket in that case. Now, coming to probability of A intersection B intersection C, we need a ticket with number having 1 at all the 3 places. That means we must have a ticket, or the chosen ticket must be a ticket with a number 1, 1, 1. But in our sample space, we do not have such a ticket, or in the urn there is no such ticket with number 1, 1, 1. Therefore, the probability of A intersection B intersection C is equal to 0. Now, we can write probability of A intersection B is equal to 1 by 4, which is 1 by 2 into 1 by 2, and which can be written as probability of A into probability of B. Similarly, we will get probability of A intersection C as probability of A into probability of C, which is also 1 by 4, and probability of B intersection C as probability of B into probability of C, which is also 1 by 4. So here we can see that the events are pairwise independent, but probability of A intersection B intersection C is a value 0. That means it is not equal to probability of A into probability of B into probability of C. Why? Probability of A into probability of B into probability of C means 1 by 2 into 1 by 2 into 1 by 2. That is 1 by 2 raised to 3. That is equal to 1 by 8. So, the second condition of our definition is violated in this case. Only the first condition is valid. So, since the first condition of this independence of 3 events is proved, we can say it is pairwise independent but not mutually independent. So, therefore, the pairwise independence does not imply mutual independence. But if it is mutually independent, then we can say it will be pairwise independent also. So, thank you.